I'll go ahead and take the time now to thank everybody for joining us today. We're really happy to be doing this. This is our first time doing a kind of webinar, so it's pretty exciting to do this. I hope that everybody is staying safe, and we all acknowledge that the times right now are very strange. I did want to comment now that Beta is fortunate enough to support so many vital industries that we are open for business, and we're very fortunate to be open. And if anybody was concerned about whether or not we are open, just know that we are, and feel free to reach out if there are any samples or projects that that would want to be discussed. Like we are operating. So okay, I think I'm going to go ahead and get started. So we are Beta Analytic. Thank you so much for being here today. So this is going to be our first episode, I'll call it right now, for our webinar series. And our webinar series will be covering a lot of different topics and case studies and sort of helping people understand how you can use isotopic analysis in your work to improve your work. Mostly I focus on water projects, but we do all kinds of projects. So this presentation is going to be hopefully pretty sweet. What I'd like to do for our next 30 minutes is, first I want to set the goal. So I want to define the terms atoms and isotopes. I've met a lot of people who they're familiar with these terms, but they don't 100% actually understand how they're used in the field. So we'll talk about that. I want to explain what makes a radioactive isotope different from a stable isotope. I think that everyone is pretty comfortable with what a radioactive isotope is, but we'll review it anyhow. And then we'll talk about what delta values are. When you have a delta value, just think of a change value, but we'll go ahead and we'll talk about what that means. And then also activities and why it is these values change and what they tell us. Right, but how are we going to get there? So I'll welcome you again. For those who are not familiar with Beta, we'll review atoms and isotopes, a little bit of stable versus radioactive. In discussing stable versus radioactive, we'll discuss fractionation, we'll discuss the delta value, activities, and then for questions, we should be able to use the Q&A function at the bottom of the presentation. Well, again, welcome, and thank you guys for being here. We are Beta Analytic. This past 2019 November was our 40-year anniversary of being leaders in geochemical analysis. So we specialize in isotopic analysis. We've been doing radiocarbon for 40 years, and we're very proud to be innovators in radiocarbon. What I'm showing off here at the bottom is that we actually do certify certain products as being plant-based using radiocarbon. And really what I wanted to highlight on our left was our ISO certification. And that is an accreditation we're very proud of. And what it does is it shows and represents our competence and why you should trust us, obviously. But really, seriously, the ISO certification does certify our competence and our ability to measure all these isotopes accurately and also show that we are capable, our capabilities. So now, before we jump into all these terms and stuff, I wanted to sort of take us a little bit through time. Sometimes people are curious as to whether or not, Beta innovated some of these things. And while we have innovated a lot of things, especially with radiocarbon, I wanted to just take us through a timeline of what it means to really be measuring atoms. So I'm just going to take us through a couple of moments in time and how science has advanced to where Beta Analytic now is able to provide some really great services. I wanted to open up with Democritus and John Dalton. So Democritus is one of the first people to begin to describe our physical world, and then John Dalton is one of the first people to actually perform experiments and begin understanding our physical world. So Lepidus and Democritus, they define atomism. So what they're doing is trying to describe the physical world and noticing that things tend to break down to these infinitesimally small unbreakable parts. Now, of course, we know that there are subatomic particles, but what I want to focus on is our description of the nucleus itself. So 1,000 years later, John Dalton picks up this idea of atoms, and he begins doing a lot of experiments making compounds, making gases like water and carbon monoxide. And what he describes is an atom being a sort of sphere, right? And his sphere, he finds it can break in and come together with different atoms. So he's basically finding that if you have carbon and oxygen, you can make carbon monoxide, and then they break down back to carbon and to oxygen. So he was the first one to begin to really describe the atom as a sphere. Up next, we have J.J. Thomson. So J.J. Thomson's work is really critical because he's the first person to actually show that magnetism can begin to move and change these atoms. He's actually the developer of the mass spectrometer, a tool that we use all the time and every day. It's an excellent tool that we use and has been honed over the years. What's really important about J.J. Thomson's work is he describes the atom as being something that is electrically charged but stable. And he has the plum and pudding model, where what he describes is a matrix of positive matter, and then inside of it, little plums of negative matter. Now, while that interpretation wasn't perfect, what it did allow us to do is begin to measure and look at atoms in a different way. He's also the first person to notice that if he changed magnetism, he can actually get a beam of what was pure gas to begin to move. So he's the first person to suggest that maybe there's a thing as stable isotopes, or an atom existing in more than one form. And I'll review that more with you, but I just wanted to take you through the timeline. Right, a student of his is Ernest Rutherford. So Rutherford works with J.J. Thomas, and what he does is he does a lot of work. So first, what he does is he studies nuclear decay, and he begins to discover that atoms are actually sort of trying to find a nice neutral charge, and in doing so, they'll actually emit radiation. And he discovers alpha and beta radiation, and he discovers that atoms are changing from one form to another, right? And that's radioactive isotopes, radioactive decay, right? He describes half-life, but really what's most important as far as this conversation is his gold foil experiments, where he found that atoms would actually bounce back and off. And as opposed to having a plum and pudding model, he describes the atom as having a centralized positive nucleus. And he works with Sir James Chadwick to discover and describe the neutron, the no charge atom. And that's where I'm going to leave atomic theory for now. So don't worry, it's not going to go crazy. I just wanted to highlight the fact that for over 100 years now, we've understood the nucleus, and we've been measuring atoms in a variety of ways for different reasons, and I'll get into the reasons in a moment. Um, I just also wanted to come in here that there was a lot more work done by Bohr, the orbital theory of electrons, and then Schrodinger describes also electron valences and clouds. So there's a lot more work done in atomic theory. But what I wanted to highlight here was that we've been investigating and trying to describe our physical world using and measuring atoms for a very long time. The last person I wanted to bring up was Harold Urey. So Harold Urey, he takes all this work that's been done before him, and he suggests, well, if there are differences in these isotopes, maybe it's a way that I can concentrate these heavy isotopes. And what he does is he performs several experiments showing that he actually can isolate these different isotopes and proves that they can be done over and over. He's also the father of isotope tracers, isotope and diet. He did some really great experiments where he had mice eating dosed organic matter, and then he found that their flesh and bones actually represented what they ate. And that's really big in Paleolithic and Paleologic investigations, understanding diet and migration patterns. Um, I also wanted to come in here that Urey also worked in understanding our primordial Earth. He and one of his students, Stanley Miller, did experiments where they took all these basic atoms and applied electricity and showed that you can actually build amino acids and stuff like that. And I just wanted to highlight Harold Urey because he sort of takes this real high-level physical thought and he begins to apply it to our everyday world and to our environment. And that really takes us to the point of being able to provide the services that we provide today. So, we are on the shoulders of giants, as they say, as I think Einstein said. Anyhow, and beta analytic uses all of this information, but for what? At what end, right? So why did I bring up all this atomic theory? Well, what we do is we use all these historic innovations and cutting edge technology to measure these atoms. And in doing so, we can answer a variety of questions. So I really love this figure, and I recommend the paper by Matos and Jackson. It came out just this last year. And what they do is they describe how isotopic measurements can be used to discover the origin of different pharmaceuticals, of different, of natural honey, or in this case honey, but of fraudulent or authentic foods. You can also use it to trace diets, like I mentioned before. But pretty much what's great about this kind of work is that it's sort of limited to your creativity. If you're looking for a change, you can potentially measure the atoms and see if that change really happened. And by measuring several different changes, we can begin to understand our physical world in ways that we could not before. So, that's pretty much why I wanted to go over the history with you so you guys can get a feeling for this science being well established and also very well honed over the last, nearly 100 years. Okay, so stable isotopes. So what was J.J. Thomson, what did he really discover? Well, what he was describing and discovering in his work was that you actually do have different forms of the same isotope, and those are referred to as stable isotopes. So what we have is a variation in mass. Now, what that means is that the reactivity, overall reactivity is the same, the hydrogen is hydrogen, but what it does mean is that one has a heavier mass than the other, and what that can do is it can make weaker and stronger bonds, right? But I really like this picture at the bottom. I think it kind of represents pretty easily. You can see that the protium, the 1H, is half the weight of the deuterium of the 2H. So you can see there that you have the same element with slightly different masses. Now, what fractionation does, and what fractionation represents, it's the differentiation of these isotopes between two phases. So the example that I like to use is a glass of water, and I'll show you in a moment. But we have kinetic fractionation that describes unidirectional reactions. So evaporation of a cloud into the atmosphere, gone forever, right? And then equilibrium fractionation, which would be that glass of water again, but capped. And what you'll find is that the water ions will actually balance between the liquid and gaseous phase, and it will equilibrate with the two substances. And then what we're finding here is that the bond strength and therefore the rate of reaction is faster for the protium, for the proton all by itself, and it's slower for the deuterium, the proton, and the neutron together. And that's because the bond strength is stronger in the heavier isotope. Now, when we talk about heavy and light isotopes, we use terms depleted and enriched. So depleted just suggests that it's less than the standard or another value, and enriched refers to it being greater than the standard or relative to another value. So here's the image that I was describing before. I think it's really clear here. What we would expect is the liquid phase to have more of the deuterium of the two H's because they're reacting less to this phase change, and then we would expect our vapor to be much more depleted or have many more 1H's or protiums present. Now, when we are describing these change values, we use what's called a delta notation. And this is I think only the heavy math we're going to talk about. It's not too bad. But ultimately what we're doing is we're measuring the ratio of the deuteriums to the protiums, and this can be done for any element. It would be the rare over the common of an unknown, and we compare that to the same ratio for the standard. And what's really great about using this method is that these standards are both internationally and nationally certified, meaning that any work done around the world can be compared to work in other places. And that's really valuable when you have very large scale projects taking place and you're trying to understand things at, let's say, a watershed level. To know that what you measured somewhere in Brazil can actually be compared to something that you measured in Australia, for example. So the actual delta value is referred to as, it would be del 2H here, and it would be an expression of how different the unknown was to the standard, and then they're in parts per mil or parts per thousand. Those are the units that we use, right? And what are some of the applications? So in hydrological studies, we can use hydrogen and oxygen to begin to identify quantity and sources of water. What I do a lot in my projects are nutrient source tracking projects where we track pollution and excess nutrients. We can use nitrogen, carbon atoms, boron, and lead. Depending on the investigation, we would pick the isotope that's the most appropriate. And then there are also paleo temperature and paleo pH projects that can be done with some of these isotopic ratios. And here in the figures, I have represented projects of non-point source and point source projects where we would use the stable isotopes to determine if we have a point source where it's coming from or a non-point source and what those variety of sources can be. And then I also have some groundwater examples here where radiocarbon can be used to determine whether or not there's been a change in hydraulic head, which is very useful with quantity. So those are two water examples. Okay, so you made it. You made it through stable isotopes, right? So just a quick review, a stable isotope is a variation of the same element. It has a different number of neutrons, so it has a different mass, but it is the same atom. It's just that the deuterium, the heavier isotope, is likely to make a stronger bond than the 1H. We use the delta value to express these changes. and we refer to positive values or positive compared to another value as enriched, and negative or negative compared to another value as depleted, right? So it's not so bad, right? Not so bad. Okay, so up next is radioactive isotopes. Now, what's fundamentally different, and this is what Rutherford was studying, was that as opposed to having the same isotope with different masses, you actually have an atom that is unstable. And in an effort to become neutral, it starts to emit this energy, and it can be beta decay, alpha decay, or gamma rays, or sorry, alpha rays, beta rays, and gamma rays. And what it's doing is it's pitching out a bunch of different energy to find its stability. Now, what's really interesting about this is that while we can't predict which parts of the atom are going to go, there is a characteristic amount of time that we expect half of the radioisotope to turn into the neutral isotope, right? And that for radiocarbon is about 5,730 years. So when we talk about radioisotopes, we refer to activity. So activity would mean if we had 10 grams of carbon that was modern, we would expect it to be very active, it'd be decaying actively. And as time progresses and as we go on to things that are what we refer to as radio dead or less active, the activity would drop over time. But because they drop in these characteristic half-lives, we can actually interpret the amount of time it took before we measured it for this carbon to have been on the planet. Now, we refer to parent and daughter. So for beta decay, the parent would be the C14 and the daughter would be the nitrogen 14. We refer to that as radiogenic, meaning that it was born of that isotope. And radiogenic isotopes can be stable, or sometimes it can also be different versions of radioisotopes as they decay on. It all depends on the atom that you're looking at. Righty, and so what I wanted to discuss a little bit here, because I think it's pretty interesting, is radiometric dating results. So what we're doing is measuring the activity, and what that does is it gives us a result in time. And first, what we do with radiocarbon results is we look at this y-axis here, and this is radiocarbon determination BP. And what that's suggesting is how much, if there was an absolute value of carbon, of radiocarbon, how old would this have to be absolutely, right? Now, once we have that, we have to accept the fact that due to the Seuss effect, which is dead radiocarbon being released by fossil fuels, and then also the nuclear bomb tests, which actually brought a lot of active radiocarbon into the atmosphere, that we have to make corrections for that. So this blue line that goes across this chart here, what it does is it shows a tree ring correction from the 1950s and estimates the amount of radiocarbon present. So then finally, at our calibrated date, what we can say with the most certainty in a 45% probability with a 78% certainty that this particular sample was likely between 987 and 10,047 years old. And for archaeological investigations, this date can be very useful in understanding and interpreting the area, the timing of an event, how old sometimes they refer to the area and to the people as different things. So you can compare the environment to the people. Are these people who are inhabiting a place over and over, or is this a new inhabitants? And then also for dating waters, it's a very useful tool in understanding the residence time in waters. And then also if we would expect a water to consistently be 1,000 years old and suddenly it changes to 500 years old, we can assume that there's been a change in the hydraulic head, which I had mentioned before. Righty, and then so some radiogenic applications. So GeoChronological studies, carbon, uranium, thorium, strontium, these all help put things in their place and time. Groundwater studies, we can use the radiogenic isotopes of strontium, carbon, and lead to do investigation as far as plume extent and impact assessments. And then something that I had mentioned at the beginning was the bio-based content. So we can suggest how plant-based a product is, whichever the product may be. It could be a toothbrush or a soap. We can measure that radiocarbon and suggest whether or not this is sourced from a modern plant or a petroleum source or a blend. Okay, so again, you guys are doing great, right? So a quick review, we have radioactive isotopes. They're different in that as opposed to being the same with different masses, they're actively changing from one to another. We measure activity. Activity gives us an idea of time. Activity reduces over time because there's less of the radiogenic isotope or the radioisotope left. And then these time periods are referred to as half-lives, and we use the terms parent and daughter to describe them. Alrighty, so our goals for this were to define atoms and isotopes. So we know atoms are elements and they're pretty much the smallest divisible pieces of our physical world. We're not getting into subatomic particles, but they are there. And then isotopes. Isotopes can either be stable, meaning that they have a mass difference and they're likely to make stronger and weaker bonds. And then we have radioactive isotopes that are actually actively decaying from one atom to another over time. And then the delta value we use to describe the changes in stable isotopes. And then finally, the activities we use to help us interpret the time that a radiogenic isotope has been decaying. All right. Excellent. Okay, so what I'm going to be discussing next, so now that we have this foundation, we can actually really get into a lot more interesting case studies and really describe how this stuff works in action, isotopes in action. So for our next presentation, what I'll be doing is discussing water isotopes and fingerprinting, and then also I'll be showing some case studies where water sources were actually identified using these fingerprints. And that's what I have for you guys today.